Hello, Assalamualaikum, and good day, everyone. So I will carry on with chapter 1, part 4, okay, which is the discrete time and signals and system, okay. So the content will be introductions of discrete time signal, DT, why we need DT signals, sampling, discrete time signals. We'll discuss about representation, the type, the arithmetic, time reversal, and time shifting. And we go next to the discrete time system for linearity, time invariant, causality, stability, and memories. Okay, if you see, some of the words are familiar because we have previously discussed in our earlier chapter, in our earlier weeks of lecture. Okay, so what is discrete time signal? Okay, as the word may suggest, discrete time signal is defined only a discrete instant of times. So means it is not continuous in terms of time axis, and it is only defined a discrete instant. For example, every 1 second, which means 1 second, 2 second, 3 second. So how about the other way? How about the other seconds like 0.5, 0.8? We don't have value there because it's only defined only a discrete instant of time. It represents as x in bracket of n. N may assume only integer value. Okay, so this is for discrete time. But if it's continuous, we will have a small t inside instead of n. But for discrete time, we have an n here. And assume only integer values. Each value is in the sequence is called a sample. Okay, we have later on we have values inside here. Okay, the values are called sample. Since most signal encoders are analog in nature, digitization is required. Okay, we live in a world, okay, where analog signals are existed in nature. Okay, digitization is what we made. Okay, so that's why we need to digitize our analog signal. Okay, digitization consists of the process sampling and quantizations. Okay, look to this graph. Okay, look to the graph. Okay, you can see quantizations and you can see sampling. Okay, so quantization is the value of the signal at discrete time is rounded at the nearest integer. Okay, so this is where we quantize the value of signal, we quantize the amplitude. Okay, at discrete time is rounded at the nearest integer. Okay, so this is our quantizations. Okay, this is our quantizations. And next is a sampling. The sampling, the signal is sampled at discrete time. For example, here it is sampled here, it is sampled here, it is sampled here. And if you realize there is no sampling for in between, okay? So that's why it is a discrete time because it is not continuous. We only sample at a discrete time which is set by us, okay? You can define, for example, every 3 seconds, the sampling, okay, 0, 3, 6, 9, and so on. So discrete time signal quantization, we converting continuous value to discrete values. Okay, so quantizations, we convert the continuous value. We have continuous value here, right? Continuous amplitudes, okay, continuous. Then we convert this continuous value to our discrete values. So if you see here, the original analog signal look like this, but the resulting discrete time signal is like this. They cannot mimic the 100% as the analog continuous signal because we have to sampling and quantization to it. Okay, But later on, I'm not sure if we're going to cover. The closer the sampling that you do, the more it uh, look closer to the actual signals. Okay, the actual original signal, which is analog and continuous signal. Okay, but if you can see, we at least we see some representations here. Okay, it follows the trend of our original analog continuous signal. So sampling, as you can see, it is sampling over, okay, over a discrete time value. Okay, so why we need discrete time signal? Okay, DSP, digital signal processing, is more versatile than analog signal processing. Okay, second, many communication systems are based on the transmissions of discrete time signal for a variety of reasons. Okay, so many communications, they are based on transmission of discrete time signal. So that's why we need discrete time signal. Sampling a signal allow us to store the signal in discrete memories. Okay, when we do samplings, we're able to store the signal in discrete memories. I think you guys also learned a bit in the digital electronics, okay, where we can store digital signal, right? Okay. Next, the output of certain sensors that measure physical variable are discrete time signal. Okay. So we have, if we want to use the sensors that measured physical variable, for example, temperature sensor, okay, many other sensors, uh, the output of it are discrete time signals. Okay. A complex algorithm for automated control physical system require digital computer implementations. The controlling signal from the computer are discrete times. Many consumer products such as CDs, DVDs, digital cameras, and MP3 use digital signals. Okay, so I think this one is you're quite familiar with all these modern items. Okay, but but I think you see CD and DVD may not be that modern anymore, because since we have our laptop are not comes with the CD and DVD slot anymore, the newer laptop. Okay, so how we perform this sampling. Okay, how we perform this sampling. If you can see, this is T is come from um, our analog continuous signals. Okay, so continuous times in S in our seconds is this one, and discrete time integer, okay, also called sample. So, and this is your N, and you have sampling time with each S. Okay, the sampling time that you are you perform this sampling. Sorry for the delay. I want to check on something a bit. Okay. Okay. So if you see, this is T, the analog, and this is your sampling, and this is your sampling time. Okay. This is okay sample, and this is your sampling time. Okay. So signal representations, for analog it is continuous, but for digital it is discrete. Okay. You see, see this out input and output. Okay, and this is our transformer there. So the transformer is an analog to digital converter. Okay, normally short term as ADC. Okay, so whenever you see ADC and see from the context of the word, maybe it means analog to digital converter. Okay, so if you see here, okay, this is our input, which is continuous signals. Okay, we have continuous signal as our input. Okay, then it is xt. Okay, we term it as xt. Then it goes through this ADC. Okay, where sample the signal at equal time period t. Okay, equal time period t, and convert the sample to the binary code. Okay, then the output you have x inside this n. You see, right? So this one is analog, this one is discrete from t to n. Know the difference. Then we sample the signal values as x and ts. Okay, you see x and ts, and is an integer. So you see here, okay, it is xt, but the totality of this converted signal is x and ts. Okay, so you see we still follow the trend of the original signals in terms of shape. However, we're only sampling at discrete time values. Therefore, we only have values at the discrete time and zeros at the other non-discrete, non-sampling time. Okay, values. So if you guys have question, you guys can ask me later. Okay, next. Discrete signal representations. So we can represent in numerical methods, and or we can represent in graphical method. So if the question require you to present in numerical method, this is how should it be. And if this the question require you to do to produce answer in graphical method, this is how it should be. Okay. So you see here xn, okay, xn 213001. So this is the numeric method. So the arrow here, okay, show that the position at n0, the beginning. Okay, if no arrow showed, this first sample hold the position at n0. Okay, let's say if we don't have arrows, okay, if we don't have arrows, the first value at the left, okay, the first value, the same first sample value usually is n0. So sometimes question can be tricky, they don't provide arrow here, for example, then you should know where is your n0. So should be the one that the first sample, okay, is your n0 if they didn't provide the arrow. Graphical method is the other way to represent our discrete signal, which is, for example, here, okay, the length of the above signal is 6. The 0 is counted if sit between non-zero. Okay, if you see here, we have a graphical method, our signals, discrete signals. You see at n0, it is 2, at n1, it is 1, at n2 is 3, at n3 is 0, at n4 is 0, and n5 is 1. So the length of this signal is actually 6. Okay, 1, 2, 3, 1, 2, sorry, 1, 2, 3, 4, 5, 6. Okay, sorry for the mistake just now. So this one is counted, okay, even though it's 0, because it is between the non-zero value. Our non-zero value is 3 and 1. So it is the length of the above signal is 6. Next, okay, what is the length of these signals? Okay, so you can try this for your exercise. Okay, I won't ask you to do, but if you want a good understanding, please try to do this. Okay, and then if you have any question, let me know. Okay, let me go for the first. Okay, this one is consider what is the length of the signal. Our length of the signal here is only 1. Okay, because we only have one value here. Okay, and this one is only one value. Okay, this one is one value, and then this one is how many values, what is the length? 1, 2, 3, 4, 5, 6. So this one is 6. Okay, so how about this one? You try this, okay, for your examples. Okay, for your exercise. Now we go to the types of discrete signal. Okay, now we go to the type of discrete signals. We can have two types, which is the step signals or impulse signals. Okay, so the step signal here, you see, before in analog continuous, it is UT. Okay, now for type of discrete signal, the type is U and 1 and zeros. Okay, you can see that step signals you have for n greater than 0 or greater and equal to 0, it is 1. So you can see here it is 1 values. However, for n less than 0, it is 0. So you can see here reflected here. Okay. So, and then you can see here, okay, because this one is like a continuous, okay, discrete time continuous, you see, more than until infinity, it is still 1 because it is greater than whatever greater than 0, it is 1. Okay, in magnitude. Next is impulse signals. Impulse signals is we only have value at a certain short time of instance. Okay, so here this is your impulse. You observe again, it is n inside, not t. Okay, because it's a discrete time. So n not equal to 0. Okay, sorry. At n equals to 0, it is 1. However, other than that is 0. So you can see only at 0 we have values of our impulse. Okay, it's our impulse. So you can see here, this is more no clearer version. Okay, so next, the arithmetic operations. Okay, we can perform arithmetic operation whether it is addition, minus, divisions, or multiplications of operation signal operation, just like our analog signal. Okay, just like our analog continuous signal. Okay, so first, see, you need of course to start with the writing of the equation first. Okay, to understand. Then you can see here, this is for example our x1n. Okay, we have 0, 1, and 2. Okay, at n 0, 1, and 2, we have values of 1, 2, and n accordingly. Okay, and then we're going to edit it, or we're going to minus it, or we're going to divide it, or we're going to multiply it. Okay, with x2 signals, with x2 signal. So here is our additions. Okay, if you see here, additions. Okay, we see here additions. Okay, let's see, we go to previous examples. 1 at n equals 0 is 1 plus 1, so you should have 2. Okay, so if you see here, so you have value 2 here. Okay, and same goes for the others. How about divisions? Divisions. Okay, let's say here we have at n equals to 1, it is 2 divided by to another 2. Okay, it is 1. So 2 divided by 2 is 1. Okay, here. Okay, that's why you see it's 1. Okay, next, multiplications. Multiplication, for example, at n equals to 2. Okay, at n equals to 2, the value is 1 times 0 should be 0. Okay, that's why at 2 here should be 0 for multiplication, and the rest of them are the same. Okay, now the folding operation. Folding, just like what in we have learned before. Okay, is a mirror. Okay, it's a mirror. So we can call it folding operation. You can call it time reversing, or you can call it mirror operation. Okay, as long as you understand it. Okay, So you see here is y in bracket of your n, okay? And then if you have x and in bracket we have negative here, n, just like in an analog continuous signal. So if you have negative here, it means that inversion involved, but the inversion now is in the along the horizontal axis, and we put the mirror at the vertical axis, so as if we have mirror in the vertical axis. Okay, so you see here, okay, you see here x and -1 at n negative at n equals -1, it is 2. Okay, let's say we mirror it, means we have a mirror in here. Okay, mirror it here, so -1 mirror will be 1, and then 2 will be transferred to here. Okay, so you can see here 0, and the at inverted signal, okay, as the output yn, you can see it is 2. Okay, how about this one, 1 inverted, it will be n equals to -1 with amplitude of 1. So you can see at n equals to -1, amplitude equals to 1. Okay, you can try this exercise at your own. Okay, you close this first, and you see, you try to perform this time reversal, and you see whether you get the same answer or not. Okay, next is just another time operations. Okay, another time operation. So we have here, okay, we have here is delay operation. So we shift the signal to the right or left by nd samples. Okay, so just like our analog continuous. Okay, so you have yn is actually the time shifted of our xn signal by nd. Okay, you see here is minus, then is if we put this one in bracket, it is plus, right? It is plus. So what happened, it is being delayed, or it being advanced its time. So this is your original signals, which is our xn. Then you perform negative, and then you have the time shifted, time delay, or time shifted. Okay, time shifted or time delay is the same, or time advance. Okay, so you see -2, so it is mean it is delayed, it is delayed by 2. Okay, so that's why here 0, for example, this one n0 shifted by 2 means n2 we have value of 1, at n1 we will 1 plus 2, which is 3, will have a value of 2. So that's why here you can see 2 we have amplitude of 1, and at 3 we have amplitude of 2, and so on. Okay, so this is the case if we time advance. Okay, so minus -2, so it will be advanced 2 seconds. Okay, advance 2 seconds. Let's say this one is n0, now -2, it is -2 with amplitude of 1. Okay, so here -2 with amplitude of 1, and so on. So you can try this also as your exercise. Okay, your own exercise. Please try to try to do some exercise, and just try to demonstrate to see if you whether you understand or not. Okay, at your own personal leisure time. Okay, so this is the exercise. This is the exercise. Yn equals to xn plus x2 minus 3. Okay, you can try this exercise. Okay, you can try this on your own. Okay, let me know if you have problems. Okay, next is the discrete time system. Okay, an entity that changes or transforms signal, input signal, into another form of signal, output signal, based on specific transfer function. So this is our transfer function. Okay, you see we have xn, you have yn as the output, xn as the input. So this is your transfer function. Okay, in discrete time system, all signals are discrete time. This system can represented by the block diagram. So you see this is our transfer function. So yn equals to t transfer function, or then x, or transform, okay, transfer function, x in bracket of n. So you see here t in bracket n represent a transformation and not a function. Okay, so don't get confused, okay, later on. T is represent the transformation, okay, T transformation, or the set of equation relating the input and output is called a mathematical model of the system. The set of equation relating the input and output is called a mathematical model of the system. So this is our mathematical model of the system. Discrete time, okay, system can be classified in the following categories: linear and nonlinear systems, time invariant and time varying system, memory and memoryless system, causal and non-causal system. This is just like the term that we already know in the previous uh, lecture. Okay, first we go for the linearity. Okay, a system is linear if it's obey the superposition principle, just like the same that we learned before in previous lecture. Okay, superposition. Consider these two system. Okay, you see, this is your xn, this is your x2n. Then you have a series connection here, or we call it also cascade connection. Cascade connection, then it undergoes addition here, and then it goes to transformation to produce the yan. Okay, next we consider the parallel connections. The parallel connection where we have our xn undergoes transformations. So we have some output here, and x to n undergo transformation, and we have some output here. Together this output aided to produce ybn. Okay, for the series case, the results is yn, and for the b, okay, this is the output. Okay, the system is linear if it's both ya and ybns are the same. Okay, whether you have this in series or parallel, okay, the system is uh, linear if it's obey these principles. Okay, next, so this is your examples. Okay, examples based on the system and equation given, find whether the system is linear or not linear. So you are given this similar graph just like in your previous slide. Now we test, okay, given, if we are given this equation, okay, y n equals to x n squared, okay, then you try to test with both system, this series, with this series and parallel connection. So for the series, okay, you see, you put your x1n plus x2n square. Okay, don't forget the square because we follow the square here. Okay, don't forget it. Then when we do some expand, then you have this. Okay, the next you test with the yb. Okay, yb is yn equals to xn square, means x1n square plus x2 square. So if you see the outputs of both ya and yb are not the same, mean the system is not linear. Okay. Next, we are given these equations: yn equals to xn plus 2x n minus 1. Then you test this with your series connections. Okay, series connection xn, whatever xn you will fill with your xn1 plus x2n plus 2x n minus 1. So you fill it with 2x, and remember there is time shifted n minus 1. Okay, then you have these equations. Okay, then you perform similar equations for the yb. Okay, then you get this. then you notice that yn and yb have the same outputs. So it means that this system is linear. Please try this at home. Okay, try test with these equations. Okay, and test whether you get the same answers. Okay, so please try. Okay, because yeah, if you try, you get the benefit. If you don't try, you don't know what you did. We don't know, so that can uh, be a trouble for you. You don't know what you don't know. Okay, next, sorry. So next is we go to this DT system, discrete time for time invariant. A system is said to be time invariant or shift invariant. Okay, if a time shift in the input results only in the same shift in the output. Okay, so the system is only if you change is only time invariant. If we if the time shift in the input, okay, let's say -2, then the output only have -2. Okay, the same shift in the output. Okay, so only then we consider this a time invariant. So you see here, transformation of x n minus t will result in y n minus t. So you see here, there is the same shift. Okay, so this is a symbol of transformation. So you see here, this consider these two cases. Okay, case one, you see the xn undergo a system to produce your yn. Okay, then you get your yn here. After some, and then the yn experience delay. Okay, so yn minus t. Case two, you have xn, then is undergo some delay. So there is shifted in your input signal, which is yn minus t, and then it goes through a system. Okay, then it produce your yn. Okay, it produce your yn. Both system, okay, are time invariant provided that, okay, both system are time invariant provided that yn minus t is equals to yd. Okay, both system are time invariant provided that y and d equals to yd. So you can see here, okay, both system are time invariant provided that this y and d is equals to ydn. Okay, they are the same if they are both time invariant. Okay, if they have produced the same value of yn minus t with ydn, regardless whether we we transform this, we undergo the system and delay after, or we delay first and we undergo to the system after. Okay, they should be the same. A system that is not time invariant is time varying. Okay, so system that is not time varying is the system that actually time varying changes. Okay, you see here, for example, yn, the exponent of exn. You can see, right, if you have n1, you have different answers. If you have ex2, you will have different. So this signal is actually time varying. You can see, right, if you have ex, if n2 you have e2x, then you have e3x. Okay, so this is actually a time varying signals. Okay, so signal which is time varying, they are not time invariant. Time invariant only change when the signals are when the signal undergo change shifted in output only due to the shifted in the particular input. Okay, next, you see the examples. Okay, you see the example here. Okay, yn equals to half of xn plus xn minus 1. You can see you have time shifted here. You have the non-shifted. So we see this example first. So case 1, we transform the can see transform of shifted signal. Okay, transform of shifted signal. So y half equals to x n minus nd. Okay, you see there is time shifted, and here n minus 1. Okay, n minus 1. The original n minus 1. The original n minus 1. And you minus with t. Okay, let me see. Hmm. Okay, maybe I should wait for a while. Okay, so where were we just now? Mm. Oh, never mind. I try to paint, paint, paint. Okay, this one. So you see just now, right? You have a T. Okay, you have T. Uh, please ignore my writing, okay, because it's difficult to write using this. Okay. So you see there is delay, right? Just now. Okay, there is delay. So which signals the originally that is your half? Okay, that is your just now. Okay, your n now is become n minus d. So that's why for this one, the n we convert equals to n minus nd. Okay, this is our time shifted. And a bit just now that is before the transformation we already have a signal which is just now you can see it is already shifted. So we're going to introduce shifted transformation because due to transformation to here. So that's why you have plus here, okay, plus x, okay, and then n is actually the one that is shifted here. So you put here n minus nd, okay, n minus nd, and then you have what? And then you have minus 1. Okay, then you have your minus 1. Then you expand it. Okay, you expand it. Yeah. Okay, this is just the same. Okay, for me to then you have your plus. Then you have your x. Okay, and then you see that you have n minus your nd. Okay, n minus your nd. Okay, and then you have minus 1. Okay, then you have your minus 1. N minus nd minus 1. So this is also the same. Okay, okay, wait for a while. Okay, so then this is you then next we do the signals, which is y n minus nd. So you have half n minus nd plus n minus nd minus 1. You see here at y here, you put the time shifted. Okay, so everything here n is already time shifted, n minus nd. This one is n minus nd as well. Okay, I think there is a bit of error here. Okay, there is a bit of error here. So result when delay at the input is similar when the delay at the outputs. So this is time invariant if the both of them are the same. Okay, if whether we delay at the output or we delay at the inputs. Okay. Okay. Result when delay at the input is similar when the delay at the output. Hence, yn is a time invariant. Okay. There is a bit area here. Okay, because this one should have the same. Okay. I think this minus here, another minus is an extra. Okay. Sorry, my monitor is having I don't know what happened. Okay, wait for what? Anyway, this lecture is recorded at 1:36 a.m. Okay, maybe even the laptop are not cooperating with me. Okay, it's late already. But never mind. This is the good time for me to do recording. Of course, I need to burn midnight oil. Okay, I had to stay up in order to produce a clear recorded without the background noise. Okay, so this is one of the sacrifices that the lecturer made that maybe student didn't aware. Just to provide this lecture, we sacrifice our sleep. Okay, so if you multiply how many times that we didn't sleep and also the time that we used to mark exam. Okay, so my section may be overflowed with students, but it's okay. I will have some bit slow in marking later on, but no, I hope you guys understand. Okay, when I have delay because section is already overflowed with students. Okay, we continue. Uh, Discrete time for causal now. A system is causal if the output at any time is dependent on the input only at the present time and in the past. Okay, it is only causal if the output, remember, is depend on input at present time and in the past. Okay, only in the past, not in the later time, not the future value. Okay, all physical systems are causal, whether continuous or discrete. Okay, so physical systems are causal. You see, physical system, the system that we have, okay, they are causal, whether it is a continuous or discrete. Okay. So we see here causality is important when dealing with online, okay, practical system, because the system does not know what the future value. Okay, so system only deals with value that already known. Okay, which is can be your present value, or it can be our past value, but not future. Non-causal system is not a problem to an offline system when input has been stored earlier. Okay. So examples, okay, you see here, y n equals to 1/3 Okay, 1/3 of xn plus 2xn minus 1 plus 2x n minus 2. Okay, if you see here, this is a causal system because no future values are involved. Okay, no future values are involved. You can see minus n minus 1 means it is a time delays. Okay, it is time delayed. Okay, means later on. And then later on the times in means it is advanced, and you have n minus 2, but we don't have the n minus n plus 1. If you isolate n plus 1, it is actually n minus 1. So means the time has been in the future before, which is for example n minus 1. So if we have n plus 1, for example, the system is not causal. Okay, because system only causal, it is if it's only consists if it's only consists um, present time and the past. Okay, next, time is only represented by the square bracket, thus only current values are involved. The system is causal. You see this value yn equals to alpha n minus 1 un. Okay, so time is only represented inside these square brackets. Okay, so only current values are involved. You see there is no shifting whatsoever. It's just purely n. So this system is causal. Next, if we for yn equals to summation of from k equals -2 until 1 for x n minus k. Okay, if you see here, this is k minus 2. Okay, if you see here, it is k minus 2. If we insert the value, we're going to have n, okay, n minus 2, n minus 1, n minus 0, and n minus 1. Okay, for the case of, for example, for the case of xn minus 2, you will have n plus 2. Okay, plus 2 means it's already in the negative time, means it is happened already. So if we expand, there will be two future value, which is our at n plus 2 and n plus 1, which is actually n minus 2 and n minus 1. So if we have this future value, the system is not causal. So a system is said to be stable if a bounded input to the system will produce a bounded output, which is BIBO. Okay, this is stable. A system is said to be stable if bounded system will only produce output which is also bounded, which is BIBO here. For example, you see this yn and xn both less than infinity. Okay, where xn and yn does not have a value of infinity. Okay, because if we have value infinity, it is not bounded. Okay, at all values of n is. So stability is important for practical because no computer or any digital processor can compute infinity values. Okay, when computation cannot be done, where the system will hang or crash, it is important to keep the system stable by avoiding these infinity values. Next, so you see these examples. Okay, yn equals to 1/3 2xn plus n minus 2 2xn minus 1. You see, these outputs only depends on three values of your n, which is xn minus 1, and xn minus 1. Okay, so if you see at different of n, if xn is bounded, output will also be bounded. So this system considers stable. How about this one? In these examples, you see this yn equals to summation of from k equals 0 until n. Okay, if you can see, then xk. In this example, there is no assurance that we're going to have bounded output. Okay, because our n there is like we need to define what is n and what is that. Okay, for example, if xn is unit step, a unit step when n equals to infinity, y will have an infinite value as well. So your y infinity will have 1 plus 1 plus 1 until it is infinity. Okay, because it is a lot of infinity, because unit step is continuous, right? Continuous until infinity. If you forget what unit step, you need to revise the previous lecture or slides. Okay, so thus if it's unit step, the system is not stable. However, if our xn is actually an impulse, an impulse signal yn will always be equal to 1 for any values of n. So thus the system is stable, because for impulse function we only have values at one time only, and the others we don't have. So the system is stable. Next, discrete time system, memory. Okay, a system is to have memory if it consists of non-current input. Okay, so if we have the future value, for example, if we have something that is not belong to the current input, so this system may have a memory. Okay, so the memory, just like in the previous lecture, also known as a dynamic system. If its output at time n0, which is yn0, depend on input values other than xn0. For example, yn minus 1 plus h n minus 1. If you see, this yn is actually depends on the n minus 1, which is your time delayed, and you also have time delay, which is not a current input. Okay, if it's current, maybe you should have only, okay, you don't have the non-current. If it's a memoryless, okay, if it's memoryless, it should don't have the time advance or time delay. Okay, vector, for example. Okay, shifting. So you see here, you have n minus 1, you have n minus 1. So they are not belong to the current input. So this system is also means this system is memory. Okay, it's also known as a dynamic. Okay, a system that consists only current input is called memoryless. Okay, just like what I presented just now. It is also called the static system. So this one is the example of the static system or memoryless system. So it only depends on the current value, which is n. We don't have any other shifting, whether it is advanced or delayed. So this is the exercise. Okay, please try. Okay, I cannot know whether you try or not. Okay, you need to be honest with yourself. Okay, try this for your own good, to be prepared for example, the coming quiz, the coming test, the coming final. Okay, so please practice this for you. Okay, you see whether you try to determine whether this system bounded or not bounded. Okay, for example, like this, xn equals to un, the unit step function. You know un is not un is continuous, right? Okay, continuous until infinity. So this system is not bounded. This one is impulse, and impulse only have one value at one time. I only have one value at a certain time. Okay, other is 0, so this one is bounded. Okay, so you try with number 3 until number 10. Okay, if you have problem, you can ask me. Okay, you can ask me in the forum. Okay, I will put lecture, this recorded lecture and lecture slide inside forum. If you have question, you can put inside the forum, and other student, other friend can learn from you, and I can learn from you as well. And it is recorded because you put in the forum. So later in time, you can track it if you want, or your friend want to track it. Next, we go to this exercise 4. Okay, determine the linearity, causality, stability, and time invariant of this system. Now, combining what you have learned earlier, okay, what have you learned earlier in the previous slide for linearity, causality, stability, and time invariant of the system, you try this exercise, okay, 1 until 10. Again, please be honest with yourself, okay, try each of these exercise, okay, uh, at your own convenience time, okay. So for exercise 4, you need to determine whether, for example, this one end, whether it is linear, causal, stable, or whether it is time invariance or not. And you have 1 until 10 exercises to help you, okay, to help your understanding. So make sure you do this, okay, as well. Okay, with that, we finish our lecture. Thank you. I will share the recorded lecture and also the slide later on at e-learning. Okay, thank you for listening and have a good day.